Thunder and lightning are the most commonplace effects of electricity seen in nature. Primitive peoples thought they were a sign of the anger of the gods, but natural forms of electricity don't show themselves in many other ways. Sometimes sailors at night would see a strange light in the rigging, which they called St. Elmo's fire. And people in the north saw the northern lights, or aurora borealis. With so little to go on, it's not surprising that for a long time men knew next to nothing about electricity. It was a Greek philosopher called Thales who in the 6th century BC made the first electrical experiment. He found that if he rubbed amber with a piece of fur, it would pick up little pieces of wool or fluff. He thought this was some kind of magnetism, but later it became known as electricity, from the ancient Greek word for amber, electrum. For hundreds of years, man learned very little more about electricity. Then, early in the 18th century, a Frenchman named Dufay came to the conclusion that there were two sorts of electricity. One could be got by rubbing amber and other resins with a piece of fur, and the other by rubbing glass with silk. The unlike kinds attract one another, but the like kinds repel one another. This was the first time that electricity's power of repulsion had been noticed. Soon after this, Benjamin Franklin proved by a dangerous experiment that lightning was electrical. He flew a kite in a thunderstorm and found that he could get a spark from a key fastened to its string. Franklin believed that electricity was an invisible fluid. He thought that when a substance contained the normal amount, it was neutral. If some of this fluid was taken from one body and given to another, the one with too little had a negative charge, and the one with too much had a positive charge. Although our ideas have changed, we still use these terms. A chance discovery by an Italian professor of anatomy called Galvani showed the way to a new method of producing electricity. The legs of a dead frog twitched when touched with a steel knife which was also touching the copper hook from which they hung. Another Italian named Volta realized that the movement was caused by an electric current produced when the two metals touched. Volta made a pile of little discs of two different metals. He found that zinc and copper gave the best results, with a piece of cloth soaked in salt water between each pair. He discovered that if he connected the top and bottom of his pile through wires to his electroscope, sufficient electricity was produced to move the little gold leaves, which you see at the bottom of the picture. He turned his pile into the first battery by putting the two metals into cups of salt water and connecting them together one after the other. So, from an accidental discovery by a biologist, new knowledge of electricity came. "20 years later, a Dane named Ørsted found that when a compass needle was near a wire through which a current was passing, the needle moved. An electric current was having a magnetic effect. Faraday reversed the process. He found that when he moved a magnet in a coil, the needle of his galvanometer showed that a current flowed. He generated electricity by induction for the first time. From this very simple beginning, all our modern generators have been developed. Faraday had given the start to the industrial development of electricity. Man soon learned to use electricity in his daily life. Numberless appliances get their current from the main supply. The current we use is carried by an overhead cable, but however closely we look at it, there's nothing to show us whether it is carrying electricity or not. Only this notice tells us that the cable is carrying 132,000 volts. Something must be happening in the wires, so let's find out what an electric current is now believed to be. We must begin in the early 19th century, when Dalton produced the atomic theory. Because we can't understand electricity if we don't know something about the composition of matter. We now know nearly 100 different elements, and scientists have arranged them in a definite order. Hydrogen, which is a gas, is the simplest element and has the first place on the table. Uranium is one of the most complex elements and is near the other end. In between these extremes are many metals. Number 47, for instance, is silver. A piece of silver, like all other matter, is composed of countless atoms. It is impossible to see an atom, but experiments have shown what it must be like. In Dalton's day, they believed that the atom was the smallest possible particle. But more recently, Rutherford and J.J. Thomson showed there were smaller particles. Through the work of many scientists, we now know what the inside of an atom is like. There is a central nucleus round which other particles, called electrons, revolve at tremendous speeds, much faster than we are showing it. The nucleus itself consists of a number of particles, but we will think of it as a single unit which has a positive charge. The electrons move round the nucleus very, very fast and in all directions. But to make the picture clearer, we will show them all moving in one plane. Their paths are not circular, they move in figures called ellipses, but we will show them moving in circles because it makes it easier to follow what happens. The nucleus has a positive charge, and the electrons have negative charges. The positive charge of the nucleus is normally exactly enough to balance all the negative charges of the electrons. The hydrogen nucleus only requires one electron to balance its positive charge. Uranium, with one of the largest atoms, has a very different nucleus. Its positive charge is over 90 times as great as that of hydrogen, and over 90 electrons are needed to neutralize it. Copper is a metal much used in electrical installations. Let's see why. The copper nucleus has a positive charge sufficient to balance 29 electrons. You see, the difference between atoms of all the elements is the size of the positive charge on the nucleus. Each atom contains a different number of electrons, but whatever sort of atom it is, the electrons are exactly the same. You might change round all the electrons, but you would not change the nature of the elements at all. They would still remain hydrogen or copper or uranium, or whatever they might be. Copper has an electron which can be freed very easily from the atom. Let's see what happens if this takes place. If an electron is taken out of a copper atom, the atom becomes positively charged, because it needs one more negative electron to make it neutral. And the negative charge of the electron is just sufficient to balance the positive charge of the rest of the copper atom from which it has been taken away. It is now neutral again. This diagram represents the atoms in a piece of copper. Each atom has one electron which is held very loosely, so loosely, in fact, that it can hardly be said to be held at all. The electrons wander about from one atom to the next. It's these free-moving electrons which make copper a good conductor. When a current starts, there is a movement of electrons. The electrons repel the electrons nearest them, which in turn repel others, and so on, right the way along the conductor. The movement can be started by chemical means, as in a torch battery, or mechanically as at a power station. But the result is the same in either case. There is a regular flow of electrons along the conductor, and it's this flow which we call an electric current. As long as the stimulus continues, the flow of electrons continues. Let's look at a complete circuit. In an electrical circuit, we have a means of starting the flow of electrons, for instance, a battery. There are wires of copper or another good conductor to carry the current where it is required. The electrical effect is caused by a stream of negatively charged electrons which flows through the circuit. To sum up, an atom consists of a positively charged nucleus which will counterbalance a definite number of negatively charged electrons. If for any reason an atom loses an electron, it is no longer neutral. It has a positive charge. The electron which the atom loses is negative. It is the movement of electrons which accounts for all the electrical phenomena we see around us. So the atomic theory explains most of the things about electricity which man has been trying to understand since Thales made his first discovery about amber thousands of years ago.